This is part 2 for week 2 and week 3 lecture combined together. Now we will learn about these three angles: solar, altitude, zenith and azimuth angles, which are used to precisely describe the sun's position in the sky. If you see the altitude angle, it is the angle between the central sun ray that is falling on the horizontal plane. So this is the horizontal plane and the central sunlight is coming from the top. So the angle here is alpha. Then comes the zenith angle theta. Zenith angle tells us the sun's elevation. So it is kind of complement angle to the angle alpha. And the azimuth angle is defined as the angle measured on the horizontal plane to determine the sun's location on the horizontal plane. Let us recap again about these three angles. Altitude angle alpha is the angle between central sun ray and the horizontal plane. Zenith angle theta is a complement angle to altitude angle, and it is used to describe the sun's elevation. So if your zenith angle and altitude angle, since they are complement to each other, if say for example I pick a value of altitude angle to be 40 degree, so the zenith angle will be 90 minus 40, which is 50 degree. So you can see that this is how, if you know one of the angle, you can calculate always the others. For finding azimuth angle, we have to find the positive direction from the north pointing coordinate axis to the projection of the central sun ray onto the horizontal plane. So we go clockwise in this way. So if this is the north, so I'll move clockwise. 90 degree will be the east, then 180 degree will be the south, while west will be on 270 degree. Then back to north again, we come back to either 0 or 360 degree. Now let's talk about magnetic north. Magnetic north is the direction when the compass shows us the north, right? But actually the polar north, or which is the geographic north of the earth, the solar module must be in line with that true geographic north. So this direction from a point on the earth's surface to the north pole along the earth's surface. That's why we have to consider the magnetic deviation. So there is a difference between the two due to the deviation in the magnetic flux lines at different places on earth. So there is a value for magnetic deviation and we can fix it. Let's try figuring out the magnetic deviation in Kuala Lumpur, is where I'm located right now. So you can see that the value given for magnetic deviation in Kuala Lumpur is 7 degree 26 minute east. That means if you are holding a compass here in KL, Kuala Lumpur, the north in your compass will be showing you 7 degree 26 minute away from the true north toward the east direction. Then how do we fix it? We take this magnetic north direction to the reverse to the true north by 7 degree 26 minute. So there is a handy rule that east is least and west is best. That means if you see your magnetic north is east, you should be subtracting it to go to the true north. And if you see your magnetic north is on the west, you should be adding it up to reach to the true north. So now it is your turn to calculate the magnetic deviation in Jabalia. So the information has been extracted from internet. You can see the declination is positive east by 4 degree 55 minutes. So remember that handy rule, east is least and west is best. Now we see the geometrical effects. Latitude. time of the day and season all affect the amount of solar energy impinging on a surface laid flat on the Earth's surface. Let's see effect of varying the tilt angle on solar capture. As we see here that the flat surface laid on the Earth like this, and when the incoming rays from the sun, I just count 12 rays from the sun, we can see if we lay it flat, it will capture only 1, 2, 3, 4, 5, 6, 7, 8, 9 solar irradiation, right? But if we are pushing it up and having a tilt angle where the flat plate will be facing the incoming sunlight at a perpendicular measure, it will be capturing most. So instead of 9, it will be capturing all the 12 solar rays coming from the sun. And this effect of this varying tilt angle, right, this one is called cosine loss. Now let us see how this cosine loss will affect if we imagine a plate that is located outside the Earth. So you can see that we are imagining a flat plate which is parallel to the surface of the Earth, and the radiation that is coming from the sun is the solar constant. Remember, we just learned that solar constant that reaches the Earth's upper surface. So if I place this plate, imaginary plate, parallel to the surface of the Earth, and can you recognize this theta z or zenith angle? Remember, zenith angle is the angle with the normal to the surface of the Earth. So we can see that now if we rotate this plate by theta z, by zenith angle toward anti-clockwise, then it will be able to receive the entire amount of I naught according to the aperture of that plate, right? So we can say that the radiation falling on the tilted surface is actually the cosine of the I naught or the solar constant. So on a horizontal surface, the effective irradiance is reduced by the cosine of the zenith angle. So I naught H is the radiation falling on the tilted surface, and I naught is the solar constant or the extraterrestrial solar radiation, and theta z is actually the zenith angle or the angle between the two surfaces. So after we saw the effect of cosine loss, we understand that designing a tracking device that can track the path of the sun for the whole day is very important. So for a solar module to obtain maximum power from the irradiance, it must always be facing the sun. So this could be achieved by the use of a tracking device which follows the sun. Now we will talk about the intensity of radiation emitted from the sun. So this intensity emitted from the sun has a spectrum that resembles a black body radiation at a temperature of 6000 Kelvin. Now the actual intensity spectrum on Earth's surface will definitely be controlled by all those absorption and scattering effects after it enters the atmosphere. So before entering the atmosphere, we will have one category of intensity spectrum, and after it reaches the Earth's surface, it will achieve another value. So it is quite clear that on a clear sunny day, the light intensity arriving on the Earth's surface is roughly 70% of the intensity above the atmosphere, right? And if it is cloudy, the amount of light intensity will decrease depending on the presence of scattering and absorption particles like water vapor, dust, etc. Before we move to the solar spectrum, we need to know some terms. I'm going to show it one by one. AM0, in short it is called, or in details it is called air mass 0. This is somehow related to zenith angle again. The integrated intensity above Earth's atmosphere gives the total power flow through a unit area perpendicular to the direction of the sun. So if I want to draw it, so if I consider a unit area that is perpendicular to the direction of the sun, so sunlight is falling on it like perpendicular one, and the integrated intensity, this area is located above the sun's surface, so we can expect that the irradiation that is falling on here will have the value of solar constant I naught. Right, so this quantity that is falling here on unit area is called the air mass 0 radiation. So it is approximately constant at a value of 1.361 to 1.367 kilowatt per meter square, depending on the measurement here, because sun's distance from the earth will vary according to the months of the year. Earth revolves around the sun in an elliptical manner, so that's why there will be a variation of the solar constant as numerical value. Now we will look into the condition when the solar irradiation enters the Earth's surface and its atmosphere. So considering that air mass 1 is indicated as the shortest path through the atmosphere is when the sun is directly above that location. That means the zenith angle will be 0. And the received spectrum is called air mass 1. Remember, the sun is right above the Earth's surface. So if this is the sun, it will be right above. So your zenith angle will be 0. And air mass 1.5 is the standard solar spectrum defined when sunlight passes through 1.5 times the atmosphere's vertical thickness. So if this one is the vertical, so when the sun is at a 1.5 times distance than this vertical distance, it will be called the air mass 1.5. So typically the zenith angle will become 48.2 degree. So we can understand that there will be a number of angles. In terms of all other angles, it is a good choice to express air mass as the ratio of the distances and the secant of the zenith angle, or sec theta z, or sec theta, whatever you want to say, is a secant of the zenith angle. So air mass m, we can identify this as the air mass m is defined as the ratio of the actual radiation path h, which is the actual radiation path here h, and to the shortest path h naught. This is the shortest path depending on the sun's location. So your air mass m is h over h naught. So if we consider the theta, so in that case h we can express at h naught secant of theta. So air mass m is, we can say, is air mass of sec theta. Depending on the air mass, the spectral intensity and wavelength, they can actually vary. So we are going to look into what happens for different air masses. The outside one, the blue color one, is the black body radiation at 6000 Kelvin. So you can see it's very smooth. While the air mass 1.0, it's a bit like irregular shape, and air mass 1.5, that means when the sun is even more inclined in the wavelength, and for a particular wavelength we can see the spectral intensity is dropping, plus it is becoming very irregular. So the spectrum of the solar energy represented as spectral intensity on the y-axis it is plotted against the wavelength of the light. And then we can see that if we need to find the overall spectral intensity, we need to plot it across the wavelength and all possible spectral intensity. Then we should integrate it to get the total intensity. We look closer into the light intensity. Light intensity, watt per meter square. That means the energy input per unit area variation with wavelength. So we have another factor, the wavelength. So the unit will be watt per meter square per nanometer or micrometer, and it is called the spectral intensity, or I lambda. So that I lambda, when we integrate I lambda over the whole spectrum, it will give us the integrated or total intensity, I total. For example, if we consider the spectral intensity and the wavelength plotting for this graph. So this one is the local irradiance at a certain time, 1348 hour. So this distribution, right? If we take a very small like delta lambda, and we already have the lambda in I, and then we integrate it for the whole range from 300 nanometer to 1000 nanometer, we will get the idea about the overall total spectral intensity. So for a certain case, when we take the total intensity, we want to try for the total intensity, the sum of I lambda over the whole spectrum. So there was a table, long table with all the data. So when they actually extracted the average I value for each lambda multiplied by the delta lambda, right? So this one is the lambda. So the finer you can make it, the more accurate will be your result. But in that case, if you are doing the computation, it will be very lengthy. So for the I total for that particular time, 1:48 p.m., when they plotted all the values and then do the integration, they get that it is 671.5 watt per meter square. So this one is usually read by the pyranometer, and when we place the pyranometer, it receives all the radiation and gives us in watt per meter square.